Go, Gator 1.
We're taking heavy indirect from the mob north of downtown, over.
You're inside phase line 3, Gator 1. That area was no-go.
Copy, Gator. We're here now. Advise, over.
Stand by. We have 4 Hugs on station at Angels 5. We'll assist egress north of phase line. Hug copy.
Solid 366. You got a TOT?
5 mics, Gator 1. Strobes on.
All copy.
Curious. What happens to the uranium when it impacts tank armor?
The A-10's depleted uranium DU round is an armor-piercing shell that works through a 3-step process. 1. Self-sharpening. Upon impact with armor, friction generates intense heat. The DU material uniquely shaves itself off via adiabatic shear banding, constantly exposing a fresh, sharp tip. This allows it to bore deeper than standard metal projectiles. 2. Fireball. Once the core penetrates, the intense heat causes the exposed DU to ignite instantly, pyrophoric effect, when it hits the air inside the tank, creating a devastating fireball and hot shrapnel. 3. Toxic dust. The burning uranium turns a large part of the projectile into an extremely fine radioactive uranium oxide dust. This fine toxic dust becomes airborne and can be carried by wind far from the impact site.
What happens when the ceramic uranium is inhaled?
When fine ceramic uranium dust, specifically insoluble oxide formed during impact, is breathed in, 2 primary hazards begin. 1. Retention and radiation hazard. The dust particles, being insoluble, tend to lodge deeply in the lungs, specifically the alveolar region. They are removed very slowly by the body's natural clearance mechanisms, macrophages, meaning they can remain in the lung tissue for months or years. While lodged, the uranium and its radioactive decay products continuously emit alpha radiation. 2. Slow systemic chemical hazard. Over a long period, a small fraction of the ceramic material will slowly dissolve in the lung's interstitial fluid. The dissolved uranium enters the bloodstream and travels to the rest of the body, primarily settling in the kidneys and skeleton bone. Once in the kidneys, the uranium acts as a chemically toxic heavy metal, potentially causing damage to the renal tubules, leading to long-term kidney impairment.
Do uranium parent and daughter radionuclides get ejected from the mass of uranium due to the nucleus recoil caused by the alpha emission?
Yes, absolutely. That is the core problem with internal alpha emitters, like uranium. When a uranium parent nucleus inside a mass of uranium decays by spitting out an alpha particle, the law of physics demands that the new daughter nucleus must instantly be kicked backward, like a gun recoiling after firing a bullet. This kick, called nuclear recoil, is powerful enough to 1. Break the chemical bond holding the atom in the original uranium structure. 2. Eject the daughter atom like a tiny hyperenergetic cannonball out of the parent uranium mass and into the surrounding body fluid or tissue. This means the original uranium mass in the lung starts acting as a generator that continuously pushes new, highly radioactive atoms into the bloodstream and to distant organs, like the kidney or bone.
And how could a dose ever plateau, as adjusted by the current risk model, utilizing the relative biological effectiveness plateau for alpha radiation?
Yes, you've hit on the central critique. The current ICRP risk model and the concept of an RBE/dose plateau may be fundamentally inadequate for internal alpha emitters due to the nuclear recoil effect. Here's why the dose likely never plateaus in the way the current model assumes. 1. Why the dose does not plateau. The current ICRP models for radiation protection often assume a dose to an organ, like the lung, will eventually reach a steady state, or plateau, as the radioactive material slowly clears. The model's flaw. This assumption generally works for material that stays put or clears in a predictable fashion. However, for a long decay chain like the one beginning with depleted uranium DU, the dose never truly plateaus because of the ejected daughters. Continuous ejection. The original uranium mass acts as a continuous factory for producing new, mobile daughter atoms, thorium, radium, etc., via recoil. Dose translocation. These ejected daughters leave the initial site and travel via the bloodstream to settle in new, highly sensitive organs, like bone marrow or the kidneys. New hotspots. The dose is not just decaying away in the lung, it is being continuously redistributed and concentrated into new, secondary hotspots in critical organs. Result: The total effective dose to the body does not simply level off. It continually shifts and increases in new vulnerable tissues as long as the parent uranium remains. 2. The invalid RBE/dose plateau for alpha radiation. The concept of a plateau in relative biological effectiveness, RBE, or equivalent dose for alpha particles, is based on a macrodose average. RBE is an average. The ICRP's single radiation weighting factor, text W_text R equals 20, is an average value meant to simplify risk across a whole organ. It is not meant for the microscopic reality of alpha decay. Microdosimetry overrides averages. At the cellular level, the local dose from a single alpha track or a recoiling nucleus is extreme. The effect is a hit-or-kill event. Since the nuclear recoil and the formation of new mobile hotspots maximize the chance that highly sensitive cells, like bone marrow stem cells, are hit by these localized kill shots, the actual biological effectiveness, RBE, is likely much higher than the average text W_text R equals 20. Conclusion: the simplifying average, the text W_text R, and the idea of a stable plateauing dose are likely wrong for the highly heterogeneous and translocating internal alpha exposure from DU and its decay chain. This suggests that the resulting ICRP risk model, while useful for simple scenarios, significantly underestimates the biological detriment from this type of internal contamination.